Welcome back to IT 3000, episode 15, and today we're talking about interrupts. If you've ever wondered how your CPU manages to juggle a keyboard, a network card, a mouse, and a dozen background processes without losing its mind, this is the mechanism that makes it possible. The core idea is simple. Instead of the processor constantly asking, "Are you ready? Are you ready?" A million times a second, the world just taps it on the shoulder when something actually needs attention. So let's pin down what an interrupt actually is. It's a signal, often called an IRQ, short for interrupt request, that tells the CPU to pause whatever it's doing, carefully save its current state so it can resume later, and jump into a small piece of code called a handler. Once the handler finishes dealing with whatever came up, the CPU picks up right where it left off. In one line, without interrupts, the processor would have to keep asking. With them, the world can finally speak up on its own. Now, once you have that mechanism, it gets used for 4 different things, all riding on the same rails. A hardware interrupt is a device asking for attention, your network card, disk, or keyboard, arriving asynchronously between any 2 instructions. A software interrupt is the opposite, deliberate, synchronous, raised by an instruction on purpose, and it's how a system call crosses into the kernel. An exception is also synchronous, but nobody meant for it to happen. Divide by 0, invalid opcode, page fault. And then there's the timer, the special one, ticking on a fixed schedule, which is quietly what makes preemptive multitasking possible in the first place. So let's follow one of these from the wire up. A device raises an IRQ, literally voltage on a line, and the interrupt controller decides which core should hear about it and with what priority. The CPU finishes whatever instruction it was in the middle of, it never stops halfway, then uses the IRQ number to look up a handler address in the vector table and jumps there. All of that, from electrical blip to kernel code executing, typically happens in well under a microsecond. And once you're in the handler, the clock is ticking. Other interrupts are often masked while it runs, so anything it delays is another device left waiting. To make that concrete, watch a network packet arrive. The card has already DMA'd the bytes into memory on its own, then it fires the interrupt, and whatever was running gets frozen right where it stood. The top half of the handler just says, "Got it, there's work pending," and gets out in microseconds. The heavy lifting, walking the protocol stack, waking sockets, happens in the bottom half, with interrupts back on. And here's the twist. When packets come in by the million, the kernel actually turns interrupts off and polls instead, because at that rate, being tapped on the shoulder constantly costs more than just going to look. That switch from interrupts to polling is worth pausing on because these 3 words get tangled all the time. Interrupts and polling are genuinely competing strategies. One waits to be told, the other keeps asking, and which one wins depends entirely on how often the event fires. DMA is the odd one out. It's not about who notices the data, it's about who moves it. The device shuffles bytes into memory on its own and then, almost always, raises an interrupt to say it's done. So DMA doesn't replace either of the other 2, it rides on top of them. If any of this sparked curiosity, the good news is that interrupts sit at the center of a whole neighborhood of related ideas. DMA and polling we've just touched on, but there's also exceptions, which are basically interrupts the CPU raises on itself, timers, which are how the OS gets its heartbeat, latency, which is how we measure whether all this machinery is actually fast enough, and device drivers, the code that turns a raw interrupt into something a program can use. That's where we're headed next. So if you take away just 3 things, interrupts come in 4 flavors, hardware, timer, software, and exception, but they're all the same underlying mechanism, just triggered by different sources. The timer interrupt in particular is the quiet reason your operating system can multitask at all. Without it, one greedy program would simply never let go. And remember, interrupts aren't a universal win. Once events come fast enough, plain old polling actually costs less. That's episode 15. Thanks for listening, and I'll see you in the next one.